Now this definition may very naturally look unmotivated. So let us try to understand from where we got this rather weird definition. To illustrate the idea pictorially, I will assume that this n is 2, so I have only the first two components, which I shall call x and y. So the x vector has two components. The first one is again called x and the second one is called y. Now suppose I take many realizations of these two random variables, that is, I carry out the underlying random experiment a large number of times and I get x1, y1, x2, y2, xn, yn, where for the ease of writing I have written them as row vectors. Now if I plot them in a graph paper, I will get such a diagram, which is commonly called a scatter plot. Now notice that these points are scattered or they're dispersed. If I look at these points from this direction, I will see a lot of scatter. If I look at them from this direction, all the points look like very tightly placed inside a pipe. So the dispersion depends on from which direction you look at it. Now when I want to define a measure of dispersion of all these points, I naturally do not want to take into account only a single direction of looking at it. I want a comprehensive picture. In order to get that, we shall employ a trick. I shall take a ruler and place it with its 0 mark at the origin in some orientation. So I am trying to understand what happens if I am looking at it from this direction. In that case, what I will do, from each point I will drop a perpendicular on this ruler. You can think of as if light is shining like this, parallelly sun rays. This is a screen and this is where you are getting the shadows. So when I look at it from this direction, I basically think that this point is here, this point is here, this point is here, like that. I cannot distinguish between these 2 points because both of them lie on the same line. So I get one number for each of the point, according as where the shadow of that point falls on that ruler. So I get some single numbers from each of these two-dimensional points. And I can see that these things are scattered a lot. So I want to find out that formula. I have redrawn it more clearly. So this is the ruler and this is one typical point x, y, and I plan to drop a perpendicular. I want to know what will be the value of this point along this scale. For this, I will quantify the position of the scale by drawing a vector from the origin to the 1 mark, and I will call this vector u. Now this particular thing, I already have given it a name. It is the x vector. So I am trying to find out the component of this along the direction u, which we know from standard formula. U transpose x, that is dot product between u and x, divided by u transpose u, which is the squared length of u. This is a scalar, just a number, times the vector u. Now here, u is measuring 1 unit along the line. So when I measure in units of u, this is the number that I will observe in the scale. So this thing is what I will observe here. Now here u is any arbitrary non-zero vector depending on how you orient your ruler and how much the spacing of the units are. So in general, this is nothing but a linear combination of x and y. So it is of the form px plus qy for some p and some q. P and q will be determined by what you take. We are interested in finding how much scattered these values are along the ruler. Now that it is a one-dimensional number, just a real number, I can compute its variance to get variance of px plus qy, that is just a plus b whole square formula, p square variance of x plus q square variance of y plus 2pq covariance of x and y. Now this can be written in a nice form using matrix multiplication as pq written as a row vector times this matrix 2 by 2 matrix times same pq but now written as a column vector. If you just do the multiplication, just do it, you will see that you will get this. Now this p and q were completely determined by how the ruler was placed. It had nothing to do with about the scatter of the points themselves. So this matrix, which is completely free of p and q, gives you the dispersion of the points irrespective of how you are placing your ruler. Once you know this matrix, someone gives you a position of the ruler, that is a way of looking at that scatter plot. From that you get PQ and you can work out the dispersion along that direction. So this matrix contains the entire information about the dispersion of those points from every possible direction. And this is exactly what we call the variance matrix. It is also called the dispersion matrix or the variance covariance matrix because it contains variance and covariance. In this exercise, I have given you 4 points. So this is x1, y1, x2, y2, like that, x4, y4. Your first job is to plot these things as a scatter plot in the xy plane. Now, I have given you the position of the eye that is looking down like this parallelly at 45-degree angle. Just by thinking about the geometry, you have to tell me the variance of the points as seen by the eye. And then you have to do things theoretically. You have to actually project all the points onto the scale and see wherever these points land and find the variance and check whether your guess in part 2 was correct. Just to fix up ideas, I will give you a certain length, certain unit. I will give you this length as, say, square root of 2. That will simplify certain computations. So this is the length root 2. And remember, this is 90 degrees. Now I can tell you that this hardly involves any complicated mathematics, almost mental math.